Lesson 86, greater than the trichotomy intransitive axioms and irrational roots. All right, let's talk about greater than first. All right, obviously, if I have a number that is greater than another number, it's going to be to the right on my number line, okay? So let's just quick review how to graph some of these. Now, on these graphs, especially when we get to the trichotomy and the transitive axiom, there's going to be some qualifications on the graphs. All right, so if I'm graphing something that says x is less than 3, but then it's got something that looks like this on the other side of it, this means that I'm graphing x is less than 3, but I'm only graphing those positive integers, okay? So the domain, the solution can only come from the set of positive integers. All right, so normally I would graph numbers that are less than 3. And I would do an open circle over 3 going to the left to show numbers that are less than 3. However, I'm only dealing with positive integers. Okay, so instead of showing less than 3, I'm only marking those that are positive integers less than 3. So the only things on my graph would be 1 and 2. Since they are the only positive integers, okay, remember 0 is neither positive nor negative. Okay, so since 1 and 2 are the only positive integers less than 3, those would be the only ones that we would graph. All right, let's look at another one just so we can kind of see some of these examples. All right, so I'm going to show graph x is greater than 3. And I'm going to have a domain of real numbers. All right, so I'm going to have a number line. I'm graphing those that are greater than 3. All right, but my domain is real numbers. Now keep in mind the only real numbers includes counting numbers, whole numbers, integers, rationals, irrationals. All right, so the only thing that is different than real numbers would be your non-reals or your imaginaries. Since we can't graph imaginary numbers on a number line, we can just graph this one as normal since the number line only contains real numbers. All right, so we would show greater than by going to the right. All right, let's talk about this in the terms of trichotomy and transitive axioms. All right, now, it's called a trichotomy axiom. Okay, axiom just means rule. All right, trichotomy is 3. Okay, so it's a 3-part rule. All right, and a lot of these we don't think about being true, okay, but when you start to explain them, it's kind of one of those, oh, duh, of course, things. All right, so when we're talking about numbers, okay, this is dealing with number compared to another number, all right? So when I'm comparing one number to another, okay, either the second number is equal to the first number, the second number is greater than the first number, or the second number is less than the first number. Anytime we are talking about a comparison of two numbers, one of these will always be true, okay? They're either going to be equal, one's going to be greater than the other, or one's going to be less than the other, all right? Nothing can be different when we're comparing numbers, okay? There's no other option. It has to be one of these 3. All right, when we talk about transitive axiom, we can call this the opposite, okay? So the opposite would be true. Okay. For example, in a trichotomy axiom, the second number is equal to the first number. All right, the opposite would that be if the second number is not equal to the first number. All right, well, if the second number is not equal to the first number, either one of these has to be true. The number will be greater than or the number will be less than. All right, the opposite or the transitive of the second rule, all right, the second number is greater than. If we were to change that to the second number is not greater than the first number, okay, then think about it. If a number is not greater than another number, it's either less than or equal to. All right, so the transitive axiom would then take place. A number is less than or equal to another number. All right, so we're just going to talk about how to graph these. All right, in order to graph a transitive axiom, make the statement true. All right, so in order to graph a transitive axiom, make the statement true. All right, so if it says the number is not less than another number, then in order to make it true, we would say the number is greater than or equal to the other number. All right, let's look at an example. All right, I'm going to say that x is not less than or equal to -4, and we are going to graph this in the domain of negative integers. Okay, so since we have a transitive axiom, since this statement is not true, we need to write it so that it is true. Well, if x is not less than or equal to, then x must be greater than, all right? So x is greater than -4. So now this is the statement that we're going to graph. All right, so we're going to draw out our number line. All right, now we are graphing it on the basis of negative integers. And we're graphing all of the negative integers that are greater than -4. All right? Anything that is greater than is to the right side of the number line. So we're graphing all negative integers that are to the right. Now, if we did keep extending this line, we would stop the graph at that point because 0 and 1 are not negative. Okay, 0 is neither. Of course, 1 obviously is positive. All right, so we have graphed all of the negative integers that are greater than -4. All right, let's try another one. Let's do x plus 4 is not greater than or equal to -2. And let's graph it on the basis of real numbers. All right, in order for this us to graph this, we need to make the statement true. But we also need to get x by itself. All right, just as you would in an equation, when you're solving for a variable in an inequality, you still use the same thing. You just treat the inequality symbol like an equal sign. All right, so to get x by itself, we're going to subtract 4 from both sides. All right, so x is going to be greater than or equal, not greater than or equal to -6. All right, we just subtracted 4, so now we need to make the statement true. Well, if x is not greater than or equal to -6, then x has to be less than -6. All right, so now we can graph that statement. I'm going to graph it on a number line. All right, the only stipulation is that we graph all of the real numbers. All right, and as previously mentioned, only real numbers aren't even included on a number line. All right, so we can just graph this as x is less than -6. Okay, that's all we're going to do with trichotomy and transitive axioms. I just wanted to mention that to you guys. We're not going to be doing a whole lot of it as we're coming up on the end of the year, but I just wanted to mention that to you. All right, let's talk about irrational roots. Okay, an irrational root would, obviously we're dealing with a quadratic equation if we're dealing with roots. All right, something that is irrational would be something that is not a perfect square. All right, something that cannot end in a terminating decimal. It's either repeating or it cannot be solved. All right. We talked about nonlinear equations in lesson 85 and using substitution to solve for those nonlinear equations. We're going to be doing the same thing using irrational roots. But when solving quadratic systems of equations, we have to remember that there will be two sets of ordered pairs. All right? So we need to keep this in mind. There will be two sets of answers, or two sets of solutions. When solving quadratic equations. All right, so there will be two sets of solutions when solving quadratic systems of equations. All right. Now the way that we're going to do this, since we're ending up with irrationals, all right, is we are going to use substitution and the quadratic formula. All right, use substitution and the quadratic formula. All right, let's look at an example. We'll just walk our way through this one. All right, we are going to be solving the system x squared plus y squared equals 11 and y minus x equals 1. All right, these look very similar to the ones that we did in lesson 85. Okay, but instead this time we're going to be coming up with irrational roots instead of real answers. All right, so the first thing we want to do is substitute. We want to get this bottom equation so that I'm solving for one variable. All right, so it can be either x or y. I'm going to go ahead and add x to both sides, so I'm left with y equals x plus 1. I'm going to use this equation now to substitute in for y. All right. Now, if I'm doing y squared, I'm doing x plus 1 times x plus 1, all right, which would give me x squared plus 2x plus 1. All right, so x squared plus 2x plus 1 is really what's getting substituted in for this y squared. All right, so now I have x squared plus 2x plus 1 equals 11. All right, so once we've done the substitution method, we want to get this so that we can solve it using the quadratic formula. Now, in order for us to use the quadratic formula, everything needs to be on one side of the equal sign and set equal to 0. All right, so we're going to combine like terms. X squared and x squared gives me 2x squared. 2x can't combine with anything, but I'm going to subtract this 11 so that it's going to be equal to 0. 1 minus 11 would give me negative 10. All right, so now I have the equation 2x squared plus 2x minus 10 equals 0. That is what I want to plug into my quadratic formula. All right, so I have a, b, and c. I'm going to plug them in. We've got negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so if I plug my values in, I have negative 2 plus or minus 2 squared minus 4 times 2 times negative 10 all over 2 times 2. All right, if I'm going to solve this out and work this out, okay, remember this is x equals. All right, so we're actually solving for our x value. All right, if I was to work this out, I would get x equals negative 2 plus or minus. All right, 2 squared is 4. 4 times 2 times 10 would give me 80. All right, 4 plus 84, or excuse me, 4 plus 80 is 84, and it's going to be all over 4. All right, 84 can simplify. Let's see. Let's break it down over here. 4 goes into 84 21 times. 21 can't be broken down. So this is going to be negative 2 plus or minus 2 root 21 over 4, which would actually reduce to negative 1 plus or minus square root of 21 over 2. All right, keep in mind, these are both your x values. And we have two x values here because one is plus and one is minus. Okay, that plus or minus automatically makes us have two solutions. Now, since they are irrational, that's all we're going to have, is just those two solutions. All right, so when I'm writing my answer for my ordered pairs, my x value is going to be -1 plus or minus square root of 21 all over 2. Those are my x values for both ordered pairs. All right, -1 plus or minus the square root of 2 over 2. All right, one is plus, one is minus. So you really don't even need to write it twice. Now, what we're going to do is we need to solve for y. All right, well, if we remember over here that y equals x plus 1, really all I need to do is add 1 to my irrational answer. When you write irrationals, you can write them separately. We haven't talked about this before. All right, but if I was to write this answer separately, it would be -1/2 plus or minus square root of 21 over 2. All right, so I've got a real and an irrational. They can be written separately. All right, so if I'm adding 1 to this, I can really just add 1 to the fraction in front, and that would give me a +1/2. So it's really +1 plus or minus the square root of 21. Again, it's all over 2. All right, so my y value is then going to be 1 plus or minus the square root of 21 all over 2. All right, and that is the solution. Okay, notice we have 2 x's and 2 y's. All right, you could rewrite it down here again. But since the 2 solutions are included with the plus or minus, you really just need to write it once. All right, I know that was a little confusing, and these are tricky to get the hang of. All right, you do a lot of these starting in pre-calculus. All right, so what I'm going to do is I'm going to give you an example, and I just want you to work as far as you can through this example. You should at least be able to work your way through the quadratic formula. All right, so I'm going to give you just one equation, and I want you to try this one as far as you can get, and we will check it again when we come back into class. All right, but this is the one I want you to try. Go ahead and see how far you can get. We have x squared plus y squared equals 9, and y minus x equals 1. All right, so go ahead and try that on your own, see how far you get, and we will check it when we come back to class.